All right, I've just started the recording now. Good morning. We are in partway through section 13.3. This is back to parametrized curves, and we're looking at a couple more concepts. So we've dealt with the derivative, that was 13.2, and that gave us tangent vectors and tangent lines to these curves in space. Now we're going to use the derivative and do a little bit more with it. So in 13.3, we're looking at arc length and curvature. So this is how the curve is bending in space. And then in 13.4, we're going to make the interpretation that these parametrized curves are actually defining the position of a particle as it's moving in space. And then we'll interpret the derivative as velocity vector, second derivative as acceleration, and investigate those things a little bit further. So where we left off last day was we introduced the arc length of a parametrized curve. And in some sense, that was based on this reminder of we knew how to compute arc length of parametric equations from calculus 1. Now we've just got one extra spatial dimension. So we're now in 3 dimensions, and we can do the same thing. And so that gave rise to this definition in the box, which said that the arc length along a space curve from point A to point B, or a value of the parameter t, which was t equals a to t equals b, is given by the square root of the sum of the squares of the derivatives of the component functions. But we can now interpret that as a length. So that was a nice interpretation that we had of our arc length formula. And that is that the arc length along a curve is the integral of the magnitude of its derivative. And if we think about this as a position of a particle as it's moving, then the magnitude of its derivative is just its speed. So this tells us that position or distance traveled is the integral of the speed, which is a result that we know from physics. And so then we did an example where we found the length along the arc of a circular helix. And we just applied our formula, integrating the magnitude of the velocity vector. And that gave us a value of 2 root 2 pi. And that was our visual interpretation, that the spiraling helix, if we go up one level, we've traveled a distance of 2 root 2 pi. Okay, now the next thing we want to do is introduce this idea of an arc length function. So what this is it's instead of saying, I want to know the length of the curve between 2 points on the curve, this says, no, I want to know the length of the curve for an arbitrary endpoint. So I'm going to imagine I've got a curve here drawn, and I pick some starting point. We'll call that t equals a. And we'll imagine that this is the direction that the curve is being traced out as t increases. Then the arc length function just says, well, starting at t equals a, figure out how long the curve is out to an arbitrary value of your parameter t. And if you do that for any value t, this produces a function. And that's the arc length function. So the main idea here is that in the upper limit of integration, we don't have a fixed constant, we have a variable. So this is asking for the arc length along the curve from t equals a to an arbitrary t value, which you can plug in different values for and get the different lengths along the curve. Because I've used t as a variable for my outside function, this function s, then my integration variable, which I normally use as t for these vector valued functions, we'd have to change it. So I just changed the dummy variable, the integration variable, to a u, just to differentiate it from the fact that we're using t now as the variable of integration. Or so a variable in the limit of integration, I should say. So this gives us a function, and I'll just indicate that this is the length along this curve now from t equals a out to some value t is given by s of t. With the fundamental theorem of calculus, we can take the derivative of this function. So when we take the derivative of that, we can use the fundamental theorem of calculus, which says you just If the limits of integration are constant up to the variable you're differentiating with respect to, then you just take that variable in the upper limit of integration and you pop it into the integrand. And so that's our fact. Our fact is really just the fundamental theorem of calculus. And what this fact is saying is that the derivative of the arc length function with respect to t, or how the arc length is changing with respect to t. And if you want to think about this as a particle moving along the curve, this is saying the change in position of the particle with respect to t is given by the magnitude of the velocity vector. Again, if I'm thinking of this as a particle moving, so r prime would be velocity. All this is really saying is we have two different ways to talk about the idea of speed, and they're the same. They both represent speed. So these are just two expressions for speed. The first one, ds dt, is just the rate of change in your distance traveled with respect to time. So the rate of change in distance traveled with respect to time is speed. The one on the right says you take your tangent vector to the curve, which is your velocity, and then you take the magnitude of that, and the magnitude of velocity is speed. So these are just two expressions for speed, but we're going to use this quite regularly through the rest of this section, that ds dt is just the magnitude of r prime of t. Okay, so what we've done is we've introduced a new function, the arc length function, and we've also got its derivative. Its derivative is the magnitude of r prime of t. So let's go ahead and do something with it. So this next problem says, let's reparameterize the helix with respect to arc length. Reparameterize the helix with respect to arc length. So what does that mean? Well, I've got my helix. I'll just draw one rotation of it. So there's my helix, and it continues on going and going and going. Right now, this is a curve that's parameterized in terms of this variable t. So it's r of t right now. But what does this actually mean? Well, what this means is that for every unit increment in time, in this variable t, how far have we traveled along the curve? Well, for every unit increment in t, so if, let's say I'm sitting at this point here down at the bottom when t equals 0, and I now look at where am I when t equals 1? How far have I traveled along the curve when t equals 1? Well, we're going to just scroll back to what we've done before. What we've done is we computed this value, r prime of t in magnitude. What is that? Well, r prime of t is the tangent vector, and this is the length of the tangent vector. In other words, this is speed. So this is how fast we're traveling along the curve, √2. So we're traveling at a constant speed along the helix. So for every unit increment in time, I will have traveled roughly √2 units along the curve. So I'm traveling along the curve at a speed of √2. That's what we can glean from this. Traveling along the curve at a speed of √2. So right now, maybe I'll make a note of this. Note, the particle travels along the curve at a speed of square root of 2. What we'd like to do is we'd like to reparameterize it. So use some new parameter instead of t, use some new parameter in such a way that when we travel along the curve under that new parameter, we're traveling along at unit speed. So we're still traveling along the same road. We're still defining the same curve. It's just our particle is moving. In this case, it'd be moving slower. We want to travel along it at a unit speed. And that's what it means to reparameterize in terms of arc length. We would like to find this curve, reparameterize in terms of a new variable s, so that a unit change in s results in a unit change in my distance along the curve. So a unit change in input results in a unit change of my position being moved. So that is, I'm traveling with a speed of 1. So let's have a look at how we would go about doing this. So the way we're going to do this is we're going to start with our r of t, which is cos of t, sine of t, and t. We'll take its derivative, because this is going to be a measure of how fast we're actually moving along the curve. So that's negative sine of t, cos of t, and 1. The magnitude, which we've already computed, but we're doing it again here, is root 2. So that's really where that root 2 is coming from. But what does this mean? Well, in terms of the fact we have at the top of the page, this is ds dt. So that's root 2. Okay, so that's the rate of change in our arc length with respect to time. So now what I can do is we can anti-differentiate. Antiderivative of this, and we get that s is equal to root 2t. I don't need to insert a constant of integration because this just says that when t equals 0, s is corresponding to 0. So we are standing right at this point, in other words. S and t correspond to the same point. Okay, so now we've got this relationship between the value of the parameter for the curve that we were given and a more natural parameter to use, which is the arc length parameter, so that every unit every unit change in the s parameter means I've just moved along the curve 1 unit. So now what we're going to do is we're going to take this relationship and we're going to plug this into r of t. Well, it's not really that we're plugging in. What we are doing is we are replacing t with s over root 2. So we're just noting that there's this relationship between s and t, and we're going to exploit that relationship by taking our parameterized curve. So what we're going to do is we're going to reparameterize. So I'm going to construct a new vector function, which is now going to be in terms of the parameter s. So I'll call it rho of s. Rho is just the Greek letter that is the analog of the letter r. So rho of s, what is that? That is my old vector function r, where I'm thinking of t as now a function of s. So I'm going to replace t with what its expression is in terms of s. So this would be r of s over root 2. And that becomes cos of s over root 2, sine of s over root 2, and s over root 2. So there's our reparameterization. This is still a helix. So that's the key point here, is this is still the helix. All we've done is just messed a little bit with the parameter. It's no longer t that I'm using s over root 2. So this still gives me the same curve. It's just it's being traced out at a different speed than the original one was. So there's our reparameterization in terms of arc length. So rho is a reparameterization of r, maybe I'll say a reparameterization of r, and it's in terms of arc length, in terms of s. Why have we done that? Why did we reparameterize it? In other words, what's that root 2 doing? It's the thing that makes it a unit speed curve now, something being traced out at unit speed. And so let's actually check that. We can see if that's the case. So what we'll do is we'll take, maybe I won't take the magnitude just yet, but we'll take its derivative. What is the derivative? Well, I can go ahead and compute the derivative of the vector function, the thing at the far right, cos of s over root 2, sine of s over root 2, s over root 2. And I'll see that I get this by the chain rule. I get these 1 over root 2's coming out. So we could do that, or I could just note that it is a composition. So rho is a composition of r and this function t. So I can use the chain rule. So if I use the chain rule, it's the derivative of the vector function r with respect to t times the derivative of t with respect to s. And that's the derivative of r with respect to t and over the derivative of s with respect to t. So I'll move that dt ds downstairs as its reciprocal. And now when I take the magnitude of this, what I get is it's the magnitude of dr dt, or in other words, r prime of t, over the magnitude of the bottom, which is ds dt. But those are just the same quantities. Those are both speed. So this is 1. In other words, we've constructed a parametrization that is of unit speed. So what I'll do is I'll give you a visual for this. We'll go to math3d.org. We'll just clear the page and we'll construct I'm going to construct the function first. So this is going to be our r of t. R of t is going to be this helix. So this is going to be cos of t, comma sine of t, comma t. And because I've made this a function, I'll just rename it. So this is our function. It hasn't plotted anything because I haven't told it to plot anything. This is sort of the background work. When I declare a function, I'm just declaring a function, and I can tell it what I want to do with it. So I'm going to make a parametrized curve with it, or a parametric curve. So it's actually, there's the helix right there. That's the default one. But instead, I am going to just tell it, draw the parameterized curve r of t. And so nothing really changed because there was already a helix drawn on the page. And then what I can do is I can now add a point to that. So there's a point. Instead of declaring the point explicitly by 3 components, I can say it is r of, and then I just need to specify a value of the variable t. So r of 0. So there we go. There's a point corresponding to t equals 0. Or I could do r of 1, or r of 2, or r of 3. These are all points that I get on the helix. Instead of specifying them one at a time, one of the nice things we can do is we can add a slider. So I'll add a slider, and its name is t. So I'll drag it to the top just because I like to have the sliders at the top. So this slider's name is t, and I can drag the slider, and it just changes the value of capital T. So I can use t as my value that I'm plugging into my function to create a point. And now when I drag the slider, I get different points on the helix. And they're only going from t value from -5 to 5, and then they'll reset. But now I can play it and just let it run through these t values. And we can see that the particle is traveling along the helix based on the parameter t. How fast is it traveling along? It's actually traveling along at a speed of √2. That's what we calculated. We calculated that the tangent vector at any given point has a magnitude of √2. So that's the speed at which this particle is traveling. I'm going to pause this for a second. We will construct a new function. So I'll drag this down below our current constructions. What's our new function? Maybe I'll call this a new function. Our new function is just going to be our old one. Still the helix, but instead I'm going to make an adjustment. I'm going to multiply by 2 in front of each of these t's. Times 2, times 2, and times 2. You might want to think about what multiplying by 2 does. Well, every time I increase the t value a little bit, this increases the argument for each of my component functions by twice that value. So I'm making it trace this curve out twice as fast as it did before. All right, which one doesn't it like? Oh, it doesn't like t because I forgot to tell it it's a function of t there. There we go. So now I can draw this curve. So I'll go parametric curve. That's not the one I want it to draw. I want it to draw R2 of t. And if you see what happened, it extended it a little bit. Why did it extend it? because we're tracing it over the same interval, -2 pi to 2 pi, but now it's multiplying those inputs by 2 before it plugs it into the equation of our old helix. And so it's tracing this curve out twice as fast or making it twice as long. I'm going to change the color just so you can see the difference. And I will bring the original blue one out front. So for that parametric curve, I'll give it a Z bias of 1. So that means when two things overlap, this is the one it's going to show to your eye. So that's why now it's blue and then the greens are on the end. You can do the same thing with that point. I will add a new point to this green helix. That's going to be R2 of capital T. And I'll make that point green. And now what we do is we have a point on each of the helixes. That's actually the same helix, but each of the parameterizations of the helixes. And we're going to see how they move compared to one another. And if you look, the green one's behind. Now it's passing it and moving ahead. So the green one is moving faster than the blue point. In fact, the green one is moving twice as fast as the blue point, and that was that argument of that factor of 2. We were interested in making a parameterization where the particle along the new curve traveled at a speed of 1. If I change this to 3, we're going to get it tracing it 3 times as fast. The blue one travels at a speed of √2, so now this is traveling at a speed of 3 √2. So in order to make it travel at a speed of 1, I already know it's traveling at a speed of √2 on the blue curve. So for this one, I'm going to have to divide by the square root of 2. And so that's the extra little feature that I'm going to have to add in here, is that I'm going to take my t and divide it by the square root of 2. And now when I look at the picture, I see that my green point is traveling slower than the red one. In fact, my green point is traveling at a speed of 1. So this is the parameterization of the curve, which has my particle traveling at a speed of 1. And that's a parameterization that uses the arc length. 1 unit change in the input, 1 unit change in the t in this case, 1 unit in this over here, 1 unit change in t produces a 1 unit change along the length of the curve. So this is a parameterization in terms of arc length. So that's what we've done. We haven't changed the underlying structure of the curve itself, still a helix. We've just changed the parameterization of it so that now when we envision a particle moving along it, it's traveling along with constant speed. So you may say, why do you want that? What does that even matter, whether you've changed the speed or not, if it's only the underlying curve we're interested in? Well, now I'm interested in the question of how bendy this curve is. How bendy is this curve? How is it bending in space? Clearly, there's a bend at every point. If we think we're traveling along it in our car, I'm on the blue versus, I'm in the blue car versus the green car. The blue car, it's changing direction more rapidly than the green car is. The blue car is changing direction more rapidly, but part of it is because of its traveling at a faster speed. That's why it's changing its direction more rapidly. The green point, the reason it's changing its direction is not because of its speed. It's traveling at a constant speed of 1. The reason the green point is changing its direction is because of the bendiness of the road it's traveling on. And so that's what we wanted to eliminate, this idea of how is the curve bending? It should only depend on the bendiness of the curve and not the speed of your parameterization of it. And so that gives rise to our next topic, which is curvature. So the curvature of a curve is how it's bending, essentially. And that is obtained by looking at the rate of change in the unit tangent vector to the curve where the curve was parameterized by arc length. So we're traveling along the curve at a speed of 1. How is our tangent vector changing? What's the rate of change in it? In particular, what is the magnitude of its rate of change? And that's known as curvature. So this is how much the curve is bending. So we think about what it takes to actually compute this Now, what does it take to compute this quantity? We have to do the following. We have to first reparameterize. So we have to first reparameterize R in terms of arc length S. But that means we first had to, there's even a step before this. We had to actually find the arc length function. S is a function of t. Then we had to write the inverse of that function. T is a function of S. And then we had to plug that into our parameterization of our curve R. So there's a lot of going on in step one here, reparameterize in terms of arc length. Once we have that reparameterization, then we have to find the unit tangent vector. And the unit tangent vector means we'd have to differentiate our parameterization and then normalize it. So there's a little bit going on in that step. Then we'd have to find the derivative of this. And then lastly, we'd have to find the magnitude of that, because that's the definition of curvature. There's a lot going on to actually find the curvature, because we've defined the curvature in terms of the unit speed parameterization. So we first have to get the unit speed parameterization and then do all the work on that. Problem is that's a lot of work and sometimes very tedious, sometimes very difficult. If we can get away with without having to go to the new parameterization of S and just work with the old one, we'd be much happier. And that's what this next result says. This next result says the curvature, you can actually get away with just working with the original parameter T. Doesn't have to be the arc length parameter. You can work with the original expression for your parameterized curve. And you get the curvature by taking the derivative of the unit tangent vector, the magnitude of the unit tangent vector, divided by the magnitude of the tangent vector. So why is that? We'll do a little proof of this, and then we'll do an example using it. So why is this? It's just really the chain rule. That's all it is. So I'm looking at the curvature formula in the box above. I need to know what dt ds is. But if t is only written in terms of the variable t, little t, then it means to take its derivative, I'll take the derivative through that intermediate variable little t. So that would be dt d little t times dt ds. That's the chain rule. And once we've done the chain rule, maybe I'll continue on writing this. So this means that this is dt d little t, and then I can put downstairs d little t ds. I can flip that over, put it downstairs as ds d little t. And so what that means is now when I take magnitudes, dt ds, which is the curvature, I've got an alternate expression for that. It's the magnitude of dt d little t over ds dt. But dt d little t, that's just t prime of t in magnitude. ds d little t, that's the magnitude of r prime of t. And so there's our result. It was really, again, just the chain rule. That's all it was. We wanted to take a derivative with respect to s, but we don't have it defined in terms of s. So instead, we take its derivative with respect to t and use the chain rule. So let's see how we could use this formula to compute curvature. So we're going to find the curvature of the helix. This is our example that we've been working with so far. Find the curvature of the helix. It says at a particular point, but we're going to see that the curvature is constant. It's independent of the point we're at. So we don't actually need to know the point we want the curvature at, because the curvature is going to be the same everywhere. So this formula says that we're going to need to know r prime of t. So that's going to be negative sine of t, cos of t, and 1. It says we're also going to need to know the unit tangent vector. Okay, so that means I need to normalize r prime of t. So I'll find its length first. We already know its length, it's root 2. Now the unit tangent vector is the normalization of the tangent vector. So it's r prime divided by its length. So that's going to be negative 1 over root 2 sine t, 1 over root 2 cos t, and 1 over root 2. And then we need to differentiate that. So we'll go ahead and differentiate that. That's negative 1 over root 2 cos t, negative 1 over root 2 sine t, and 0. And then we're going to need to know the magnitude of that one. So the magnitude of this vector is, well, it's just negative 1 over root 2 times a unit vector. Cos t sine t 0, that's a unit vector. So this is 1 over root 2. And so we've got all our ingredients now. These are the two pieces we need for our curvature formula. And so we have that the curvature is equal to the magnitude of t prime of t over the magnitude of r prime of t, which is 1 over root 2 over root 2, or in other words, a half. So there's our curvature of our helix. It's constant, it's independent of the point you're at. It's always 1/2. So at this point, you might be saying, what does that even mean? You know, okay, curvature, I know that that has to do with bendiness, but I don't know, is a half, does that mean it's really bendy? Or does that mean it's not so bendy? Don't really have a gauge for understanding how much this curve is actually curving, how much is bending, or what's the curvature actually mean. So a little fact just to keep in mind, and you can verify this. A circle of radius r has curvature 1 over r. You can verify this. How would you verify it? Well, you just get a parameterization of a circle. I'm going to call it A because I don't want to mess it up. Actually, yeah, I'll call it a circle of radius A has curvature 1 over A. The reason I'm going to do that is because now when I say you want to verify it, I'm going to use r for the function that will create the circle. So r of t is, if it's a circle of radius r, we could write it as a cos t, a sine t. And we could leave it there. A circle lives in the plane. But if you're worried about, you want to make sure everything's got three dimensions, then we could just pad it with a 0 on the end. So you could take that curve and go through the curvature calculation we just did above. It's basically taking the t in the expression above and making it a 0 and going through it all. And so that would verify that a circle of radius A is curvature 1 over A. So what that means is a large circle, big radius, has a small curvature, and a small circle has a large curvature. It's inversely related. So the curvature is the inverse of the radius. So this particular helix that we've got, it's got a curvature of 1/2. So that means at every point along it, it's bending like a circle of what radius? So our curvature is a 1/2. So that means it's bending like a circle, or kind of looks like a circle. At that particular point, you wouldn't be able to.
Two.
You got it, exactly. So at any particular point on this, you're driving your car along this helix, you wouldn't notice that you were on a helix other than maybe your elevation is changing. You'd be thinking like, oh, I feel like I'm on a circle of radius 2, just the way I'm bending, the way I'm sort of turning my wheel and feeling these sort of forces of the turn on me. So that's how we can interpret curvature. You can think about it in terms of the underlying circle that it's approximated by, in terms of its bend. Okay, so I want to point out one thing. The previous calculation we did, all things went fine, but there's going to be some troublesome parts if we do it for a more complicated example. Namely, the troublesome parts are to apply that formula, the one up here, t prime over r prime, the magnitude of that. When I did my calculation, I had to first construct r prime. Then I had to normalize it to get t prime. It just so happened that r prime of t had constant magnitude, so we just had to divide by a root 2. But in general, these curves will not have constant magnitude. The tangent vector will not be of constant magnitude. So we'd be dividing by some non-constant function. And then the very next step, we're going to have to differentiate that. So there'll be a bunch of quotient rules that can come in, and things can get messy pretty quickly. So we'd like to be able to find the curvature without even having to normalize. We've eliminated the parameter s, having to reparameterize in terms of arc length. Now we'd like to go even one step further and say, I don't even want to find the normalized tangent vector, the unit tangent vector. Can I do this calculation without even having to do that step? And the answer is absolutely you can. Here's a formula for the curvature that all you need is the original function r. You don't need to reparameterize, and you don't need to normalize it at any point. So how can we prove that this formula is correct? So we'll give a proof of this, and we'll base it off of our fact that our unit tangent vector is given by r prime over the magnitude of r prime. And I'm doing this because we've already got the definition of curvature in terms of our rate of change of our unit tangent vector. So I'm going to make this my starting point. So I've got my unit tangent vector. That means I can rewrite r prime as the magnitude of r prime times the unit tangent vector. But the magnitude of r prime is just ds dt. So I'm going to rewrite it like this, just because it's going to help me in my next step. My next step is to say, let's now differentiate this equation. So I'll call this equation star. And now we will differentiate star. That gives me r double prime. And that is the derivative of star, it's the product. We got the product of two things. It's ds dt multiplied by the unit vector t. So we've got a product there. So that means I'm going to use the product rule when I differentiate. So it's the derivative of the first, d squared s dt squared, times the second, plus the first, ds dt, times the derivative of the second. So there's our product rule. One extra fact that we can note, you may have remembered this fact, you may have not, is that these are orthogonal. T is perpendicular to t prime. You may say, well, why is that? Why do we know they're orthogonal? I said we can recall this fact. So the reason is, we'll go back to 13.2 notes. Where are those? 13.2, there they are. We had this result. Underneath all of our properties of differentiation rules, we had this result that said, show for a differentiable vector function r of t that has constant length. So the magnitude of r of t is constant. Then the tangent vector is always orthogonal to the position vector. So that means that its derivative is orthogonal to itself. So if I have a vector function of constant length, its derivative is orthogonal to itself. So that's perfect, because that's what I have here. T has constant length, it's length 1. So its derivative has to be orthogonal to itself. So I've just decomposed r double prime into two directions with their perpendicular to each other, t and t prime. And now what I'd like to do is I'd like to take that expression for r prime, r double prime, and we will cross, well, maybe I'll say it, cross r double prime. Well, I'll just say it this way. We'll cross r prime with r double prime. Because r double prime is made up of two directions, t and t prime. R prime is in one of those directions, t. So if I cross them, I'll get some cancellation. So let's take their cross product. When I take their cross product, I'm crossing this vector, t, with that one and with that one. When I cross t with itself, I get 0. And so only the second term survives, and that would be ds dt t cross t prime. So that's what we get when we take our cross product of r prime with r double prime. We get something that's in this direction, t cross t prime. Now what I'm interested in is the magnitude of this, because that's what's in our formula we're trying to prove above. It's something about the magnitude of this. So we can go ahead and take the magnitude. When I take the magnitude, I get the magnitude of ds dt. And well, s is the arc length, so it's the rate of change in it is essentially positive, but we'll slap absolute value signs on it anyway, just in case. So we've got the magnitude is the magnitude of ds dt times the magnitude of t cross t prime. And we know that t and t prime are orthogonal to each other. So the magnitude of their cross product is just the magnitude of the individual vectors themselves. That's where I used this fact to go from here to here, use the fact that they were orthogonal to each other, because the magnitude of the cross product is the magnitude of the two vectors times sine of the angle between them. But if there are 90 degrees between them, then sine of that angle is 1. We also have that the magnitude of t is 1. And so this gives us a nice expression for t prime in magnitude. It is r prime cross r double prime all over ds dt. But that's r prime cross r double prime, and ds dt, that's just the magnitude of r prime. And so we've got now this expression for the magnitude of t prime. And that's exactly what we wanted, because in our curvature formula, the curvature is the magnitude of t prime over the magnitude of r prime. And we've just got this expression now for the magnitude of t prime. It's r prime cross r double prime all over r prime. And oh, I'm missing a square somewhere. Where am I missing the square? Oh, that's where I was missing the square, in the cross product. Someone probably picked that up. When I did the cross product, it was this cross this. So there was two DS's there. I missed the square right there. And then there's a square here, a square here, a square there, and a square there. My apologies. I missed the ds dt multiply together. So the question in the chat, a direct message to me, was how did I get 0 when I crossed it? The reason we got 0 here was because it was essentially t cross t. So a vector, two vectors that are parallel to each other, their cross product is 0. And in this case, it was just a vector crossed with itself. So its cross product is 0. And so now we're dividing by an extra r prime magnitude in the bottom, and that's where we get our cube in the end. And that's the verification of our formula above that says we can get the curvature by just working with the original functions themselves, r prime, r double prime. So let's go ahead and use this result. We're going to find the curvature of this curve. So the idea is we first introduced the curvature as a rate of change in the unit tangent vector parameterized in terms of arc length. We got rid of that parameterization and just said we could do it in terms of the rate of change of the unit tangent vector over the rate of change in the tangent vector. Now we've got rid of the whole normalization aspect of it, and we've just said, nope, now it just depends on the cross product of r prime and r double prime in the magnitudes. So this simplifies our calculations quite a bit. R prime of t is 3, 4 cos t, negative 4 sine t. R double prime of t, just differentiate again, is 0, negative 4 sine t, negative 4 cos t. Then what we need to do is we need to take the cross product of these two. So we're going to take r prime of t cross r double prime of t. You can go ahead and set up that cross product however you like. In order to do it, I'll just write down the result in this case. The cross product is going to be negative 16, 12 cos t, and negative 12 sine t. In particular, we're interested in the magnitude of this cross product. So we can go ahead and find the magnitude of it. And that works out to be 20. So that's one value we need. And then the other thing we need is the magnitude of r prime of t, because that's going to be in our denominator. And the magnitude of r prime of t is root 9 plus 16 or 5. So that's the other value we need. And that means then that our curvature at any point along the curve corresponding to a parameter t is given by the magnitude of r prime cross the magnitude of r double prime of t all over, in this case, r prime of t cubed. So it's 20 over 5 cubed, or 4 over 25. So the curvature is 4 over 25. So that means it's bending roughly like, or curving roughly like, a circle of radius 25 over 4, the reciprocal of that. So 25 over 4, or something like a radius a little bit more than 6. So that gives us a feel for how much this curve is curving or bending at that point. So that's curvature. The facts. So part 12, the next part, fact to do with plane curves and the subsequent example, that's just a throwback to Calculus 1. I've already recorded a video, and I'll post it right after class where I do that calculation. It's about a 10-minute video. I'm not going to do it in class because, again, it's just take these ideas from 3-dimension and apply them to 2-dimension and rederive a formula that you may or may not have seen in Calculus 1 for the curvature of a function of a single variable. So there's our curvature. What are we going to be able to do with these ideas? Well, these ideas, we can translate them over to particles, functions which are vector value functions which represent the position of a particle. And so that's our next section. So we'll pop into our next section, which is 13.4. So 13.4 is now saying, let's interpret these space curves as defining the position of a particle as it's moving. And that's kind of the analogy I've been using all along, just to build intuition. So there's not much new in that context. There's a lot of text here, but really it's just saying velocity vector, what is that? So the velocity vector of a moving object is a vector which is composed of two quantities, basically the magnitude of the vector and the direction of the vector. The magnitude is what we call speed. The direction is, well, that's the direction the particle is moving in. The velocity vector is just the derivative of the position function. So it's going to be v of t is r prime. Might be hard to see, but there's a prime right there. There's a prime in that formula. It's very close to the arrowhead. So the velocity vector is basically our r prime vector that we've been using all along. And the speed would be the magnitude of that. So our speed is the magnitude of v, or in other words, it's the magnitude of the r prime of t. So I've used these terms already just to build intuition, but that's the idea. What's the second derivative? That's the acceleration vector. So we've got velocity vector and acceleration vector. So what can we do with that? Well, we can say here's a particle. It's given by this position function r of t. Let's find its velocity, speed, and acceleration. So the velocity vector is basically just r prime of t, which is 2e to the 2t, 1 over 2 root t, and the derivative of this piece here, I'll write it as a t squared plus 1 to the negative 1, just so I can use the power rule to differentiate it. So it would be power comes down, negative 1 all over t squared plus 1 squared times the derivative of the inside, which is the 2t. So I'll put the 2t up top. And so there is our velocity. What we can do next is we can work out the acceleration. That's just r double prime of t. So now we've got physical interpretations of these higher derivatives. And the acceleration, it's going to be 4e to the 2t. The derivative of the next piece is, I'll just write down the derivatives, negative 1 over 4t to the 3/2. And then the derivative of this third piece, that would be a quotient rule. And so it would be, when you finally sort of put it into its nice form, it would be 2 times 3t squared minus 1 over t squared plus 1 all cubed. I encourage you to check these to make sure that these derivatives are, as I say they are, by just using your techniques from Calculus 1 to take the derivatives. Now what we're interested in is what's going on at t equals 2. We wanted to find the velocity, speed, and acceleration. So v at 2, we just plug it in, and that would be e. So v at 2 is 2e to the 4, 1 over 2 root 2, and negative 4 over 5 squared. So that's v at 2. That's our velocity. We're interested in speed. Speed is the magnitude of the velocity. I don't want to use s for speed because we use s for arc length already. So to just talk about speed, it's just the magnitude of the velocity vector. And we can compute that magnitude, and that ends up being 4e to the 8 plus 1 over 8 plus 16 over 25 squared. So that's our speed. And then our acceleration at time 2. We just pop 2 into our acceleration formula, and we get this result here. So there's our acceleration vector. Where I want to end off with today, and we'll pick it up next day, is the acceleration vector. We kind of want to know what direction it goes in. We know what direction the velocity vector goes in. That's the tangent to the curve. That's going in the tangential direction. What about acceleration? Well, acceleration turns out to have 2 components. One component that's tangential to the curve, and that's depending on your change in speed. But there's another component to acceleration, and that's due to how the curve is bending. So that's another way your velocity vector can be changing direction, is due to the bending in the curve. So we're going to see that acceleration breaks up into 2 components. There's a tangential component and another component that's related to the curvature, and that's known as the normal component of acceleration. And what we'll see is, I'll scroll down a little bit past these 2 examples. We'll see that the components of acceleration, there's the tangential component, the component that goes in the t direction, and then another component that goes in the normal direction. The one going in the normal direction seems to be related to curvature. You can see a kappa appearing there. But even more than that, the next formula says that that normal component of acceleration, it's related to the cross product of r prime and r double prime. And the tangential component of acceleration is related to the dot product. So this is a very beautiful sort of splitting of, you've got an acceleration vector and it splits into 2 pieces. One is related to the dot product, the other is related to the cross product. And so we'll verify these facts and we'll use them, and we'll do some examples next day. Oh, and by next day, I mean that, as I said, next day, Friday, I won't be here for lecture. I'll be here for office hours. So I'm shifting my office hours into the lecture period. So what I'm going to do is I'm going to post a video that has these things worked out. And then on Friday during class time, 9:30 to 10:20, I'll treat it as office hours. So it's just going to be a question and answer period. So you have questions on this or want to work through some more examples, etc., we're free to do that. But I'll post a video for this section so you can watch it either beforehand, or if you have questions about the homework assignment, you can watch the video afterwards and ask questions about the homework. All right, so that's it for today. I will stop the recording.